Yes, well, okay, welcome everyone. The plan today is to wrap up, for the most part, maybe not entirely, our work with systems of differential equations in particular. So today I want to focus on how we can look at the dynamics of nonlinear systems. So we kind of started our study of systems by looking at nonlinear systems. Rabbits and foxes was a nonlinear system. Um, and so I want to kind of return back to those sorts of problems, how we can use all of the techniques we used with linear systems to classify stability analysis of equilibrium in nonlinear systems. So I just wanted to let you know that the homework for next week is due on Wednesday as opposed to Monday. So you have a couple of extra days to work on that, since we might need to finish up some things on Monday related to that. So I just wanted to give you a couple of extra days for that. But any general questions before we get started today? Okay, so the example I want to take a look at for today is what's called a simple pendulum. So we have, you can think about it like a clock, which is attached, and we're going to ignore gravity in this problem, or we can, and then we can just kind of look at how is this thing, sorry, we have gravity here, that's the only force acting on this pendulum, and how is this pendulum going to move over time. And so let's just kind of think about this intuitively, and then let's see how the math may or may not match our intuition. So our two variables here are the angle theta and the velocity of the pendulum. And so let's say, for example, I start at a point like right over here. So at this point, we'll say that theta is 0 and the velocity is small. That's what we mean by that. And so if I start the pendulum off at time 0, which would be like in this position, or excuse me, at theta 0, and then I give it a little bit of velocity, let's say I push it in this direction just a little bit, what's going to happen to the pendulum? Feel free to enact it with your arm on the camera. What's going to happen? I have this pendulum, right? I push it a little bit. What's going to happen? It's going to rock back and forth, right? If we give it a little bit of velocity. So what that would look like is that its velocity is going to change and its angle is going to move around. So let me just mark an angle of pi over here. So what would happen in this case, and just so it's clear what an angle of pi would mean, that would mean the pendulum is up here at an angle of pi. So pi would mean it's sitting perfectly vertically up. 0 means it's sitting perfectly down. So if I take this pendulum and I give it a little bit of velocity, it's not going to rotate all the way up to pi, right? It's just going to rock back and forth as time goes on. So it'll be a positive angle, it'll be a negative angle. We might get some behavior that looks like this, for example. Okay, so this means that the velocity is changing, the angle is changing, but it's not going any further than pi, or any further to the left than minus pi. This is kind of saying it's going to do this rocking back and forth. And then let's say instead, I start off at this resting position, but now I give it a big initial velocity. And now what might happen if we push it hard enough? is going to do the same thing. What's going to happen? Feel free to chat it in if anybody has any thoughts.
The pendulum swing is just going to be more exaggerated. If you push it hard enough, it could make a full rotation, but.
Yeah, so maybe there's like an intermediate step, right? The harder we push it, it might get closer to this kind of critical angle of pi, but it might not get there. Then suddenly we push it really hard, and this might be the case where this pendulum, we give it a big velocity, and then it might rotate around a number of times before it settles back down at the bottom. So it's going to go past pi, and if it does one rotation and then settles back down, then that might look like it's going to you know, wiggle around, and then eventually it would settle back down at its resting place. This would mean after it's done one full rotation. And you can imagine pushing it even harder, so it does 2 full rotations and then settles back down at 4 pi and 6 pi, etc. But what we do see are these like spiral sinks that we saw last time. So we do see that there are some equilibrium here, and they do, the ones that we've identified so far do seem to be stable. So for example, if we were to start at 0, 0, this means we start at the resting position and we don't push it at all, right? It would stay there forever. So that's like a constant solution. That's exactly what an equilibrium would be. And in this case, this would be stable since solutions that start near it are going to stay near 0, 0. I have been disconnected from my iPad. Hold on a sec. But any questions? Can anybody think of an example of equilibrium that would be unstable? In the sense that if you were to set it up perfectly initially with this condition, it would stay there. But if you are slightly off, then it's actually not going, it would move away from that equilibrium. Oh, I mean, what's another equilibrium other than 0, 0? There are infinite number of equilibrium in this system, actually.
In pi?
Yeah, so if we set it up at, say, like 0, I should put it like this, since the first thing is the angle, and then the next thing is the velocity. If we were at pi 0, this would mean the pendulum is situated so that it's at its vertical position. And if you were extremely precise, it's possible that you could set it up just perfectly like that, and it would stay there forever. But most likely, as hard as we try, right, we would be just like slightly off from that position. And what you would expect to happen is if you're slightly off from that position, it's going to flop back down at its kind of lower resting place. So this would be unstable equilibrium. So that would be like this point over here. If we started off perfectly there, it would stay there. But if we're off just a little bit, let's say I start here instead, well, this is going to be a very special direction, which is going to head straight in towards the equilibrium. Well, it'll have some velocity, so it'll kind of wiggle around that, but it'll head back towards the equilibrium at 0, 0, which is stable. Okay, any questions so far? Just trying to get an intuitive picture of the dynamics of the pendulum that we're working with. So there are stable equilibrium, there are unstable equilibrium, lots of equilibrium. So the idea here is when we were working with linear systems, we only have one equilibrium, which is at the origin. So when we have something that looks like this, one thing that these systems all have, these linear systems, again, is that there's only one equilibrium at the origin. And for the reading and what we talked about at the end of last class, we talked about how the eigenvalues of the system tell us what type of equilibrium we might have. When we have nonlinear systems, we can get more than one equilibrium, and then at each equilibrium, we're going to have to piece together the dynamics. So the dynamics at each of these equilibrium, they might be saddles, they might be sinks, they might be center points, they could be all of these different types. So that's going to be the plan. Our plan of attack is going to be, how can we take these nonlinear systems and approximate them with linear systems and then do the same stability analysis that we did last time. And so the kind of key to that was what you guys looked at on the reading quiz on Monday, which is tangent line approximations and things like that. So that's going to come into the picture today. So if you're kind of curious about the derivation of these equations for the pendulum, I put a video up online so you can kind of see where those come from. If you don't care, then here's the equations of motion for the pendulum. It comes pretty similarly from how we looked at the mass spring systems. Not totally unrelated to that. And so if we set it up using Newton's second law, we get like a mass times acceleration equals the sum of all the other forces. So whenever we use Newton's second law, there's an acceleration involved, and that's where we get a second order differential equation. And so for Monday's video, you looked at how you can take any second order differential equation and be able to express it as a system of two first order differential equations. And so we can do that here to take this equation of motion for the pendulum and express it as a system of two differential equations. And again, the way that we do that is we introduce a new variable v, and we define that as the derivative of the other variable theta. So that gives us this equation over here. And then using this substitution, we can rewrite this equation since we can say dv dt would be the second derivative of theta. So then we could take this term over here, the d theta, second derivative of theta, and replace it with dv dt. We could take d theta dt and replace that with the fact that that is just v. And then I can solve this equation for dv dt. By bringing those terms to the other side. Okay, just that in this case, we're not getting a linear system because of this sign. sine of theta in our differential equation. So just to simplify this, since you can see there's a lot of letters floating around, I substituted in some values for B and M, and I just set L equal to gravity, and that simplifies some of the coefficients here. So we're going to take a look at this system for certain values of B and M and the length of the pendulum, but that's where these coefficients come in. So let's think about this system over here, which again is exactly connected to the previous graph and equilibrium that we were looking at. Any questions? Okay, so then let's go ahead and now find the equilibrium mathematically, not intuitively like we did on the previous one. So here we've got a system, and if I want to figure out where are the equilibrium, just for the sake of notation, I'm just going to use primes instead of DTs. And so if I want to find equilibrium for a system like this, then what is it that we would need to do?
Set the first derivative equal to 0.
Yeah, we set which first derivative equal to 0?
Well, in this case, it'll be both of them, right?
Yeah, that's right. We want to solve when are these simultaneously equal to 0. That's right. So we need to solve a system, in this case, of nonlinear equations. So I take the top, set it equal to 0, and the second equation, set that equal to 0. So you can see from the top equation, we see that any equilibrium is going to have V equals 0 initially, right? And that makes sense. If you start to move this pendulum, then it's going to move, right? It's not going to stay at its constant position. And then we can plug that into the bottom differential equation, and then we see that V prime is minus the sine of theta, and that's going to be 0 as long as theta is some integer multiple of pi. So we actually get a whole infinite slew of equilibrium, which is relating to this fact that you could push it really hard and it can kind of rotate many times over. Okay, so this means that our equilibrium are going to be anything of the form k pi times 0. And so kind of if we're imagining the phase plane where I've got theta and V, right, then we have kind of a whole lattice of equilibrium going across for any integer multiple of theta. Okay, and as we talked about, if we have it in its bottom position and we don't give it any initial velocity, it's stable. When we position it up top over here, And you might be thinking, maybe we should expect some sort of behavior like this. When it's odd, it's up vertically. That seems very precariously balanced. That's unstable. When it's even, that means it's in its bottom position. That's very stable. And so what we'd like to do is be able to piece together the dynamics in the full phase plate. Okay, any questions so far?
So we really haven't done anything different other than just switched around variable names. We're just calling them theta and v now rather than x and y, right?
That's right.
Okay.
I was gonna ask, can you explain again why it's unstable if it's in a like pi, 3 pi, 5 pi?
Yeah, so you've got this pendulum over here. And so if you set it up in this position, so this would be like theta equals 0 and the velocity equals 0, it's going to stay there. It's not going to move. If instead we have it so that the pendulum is now located up here, okay, this is very unstable because what that means is if you were to set this up with an initial condition close to but slightly off from that so that it's not perfectly at pi, but it's like at pi minus 0.000001. So you're just like a fraction of a off from this position. A pendulum that's over here is not going to move back to that position. It's going to move back to its bottom position. So that's why it's unstable. So we would say it's stable if it moves back towards that equilibrium. We say it's unstable if it moves away from it towards another equilibrium.
Okay, thanks.
Yep. Yeah, so 4 pi would be stable, 6 pi. So all of the even powers, that was a question that came in. We should expect, based on our intuition at least, we haven't proven this mathematically, but it makes sense that we're seeing the odd ones. These are ones that are up vertically. They seem unstable. The even ones are when the pendulum is situated at the bottom, and that seems very stable. So let's see how the mathematics can reflect that behavior.
Thank you.
Yep. And so what we would like to do, again, is say, well, if I had a linear system, I know I can look at the eigenvalues of the matrix of coefficients, and then depending on the signs of the eigenvalues, that's going to tell me something about the stability. And we're going to mimic that analysis exactly over here. The problem is this is not stable. So really all we're concerned about do initial conditions very close to the equilibrium. So do these head towards the equilibrium or away? So that's generally like what we're thinking about when we say stable versus unstable. And if it heads towards the equilibrium, it's stable. And if it heads away, then it's unstable. Okay, but the idea here is that we only really care about points theta v, which, for example, are very, very close to the equilibrium at 0, 0. So if I were at like 0.1, 0.1, where would I go? And so this is where these linearizations come in handy. So if I consider the sine function then what we talked about, or at least what the video talked about, is at any given point, right, we can find the tangent approximation to that line. I'll call that L. just kind of putting this formula out there by saying we can find the slope by calculating the derivative of that function at that point. And then we also use the fact that the point that we know that's on the line is where their tangent, which is at a comma f of a. And this gives me the tangent line approximation. And what's really nice about this is, now I can actually do this, is that like when you zoom in really close to this, the tangent line and the curve are essentially equal to each other when we're really close to that point of tangency. And so when we're doing this stability analysis, we're only going to want to consider points that are really, really close to that equilibrium. So I don't care that my linear approximation is bad for values far away from that equilibrium, because this is a very local analysis. We're looking at how are these solutions behaving when we're really, really close to that equilibrium. So I just want to kind of emphasize that what we're going to do with this linearization process helps us answer what's happening really close to the equilibrium, but we shouldn't use that analysis to think about what's happening generally at other points in the plane. And so to come back to this problem, if we want to think about, well, is this equilibrium at 0, 0 stable or unstable? Then what I can do is use the fact that if theta is small, meaning really close to 0, then the tangent approximation for the sine of theta is just theta. So this graph down here, its tangent approximation over here is just, for example, y equals x, if we had x and y instead of theta and v. So rather than use this sine function, which is not linear, we can replace it with its linear approximation, which is theta. So now I can take this system from above and I'm going to put theta in place of sine theta, which is fair to do as long as we're just thinking about theta being small. And now this is linear, right? Where I could write theta prime as 0 times theta plus 1 times v, and v prime as minus theta. Okay, just to kind of set it up in a way that we can very easily see what the matrix of coefficients would be here. So this the linearization of this system has the following matrix of coefficients. And so if I want to think about is the equilibrium at 0, 0 stable or unstable, I now could find the eigenvalues for this matrix. So we're going to go ahead and take the determinant of this matrix. Not this one. And set it equal to 0. And so that would give us minus theta times minus 0.2, I have an extra. And then trying to solve that quadratic equation. So that would give us lambda squared plus 0.2 lambda plus 1 is equal to 0. Any questions with what I'm doing at the moment? And then we could try and find roots for this. So I would get this plus or minus the square root of 0.04 if I square that, minus 4 over 2 using quadratic formula. And at least at this point, what I can see is that it's going to be complex because the thing under the square root is negative, and the real part is going to be negative because of that term that I just highlighted. So we have a complex root with a negative real part, which means we should have a spiral sink. Which is exactly what we kind of first drew on the first page. Any questions? Okay, so that tells us over here, that's where that spiral sink came in. So it's kind of nice, I think, to see the math kind of mimic some of the intuition that we might have about this pendulum, like where these spiral sinks and spiral sources come in practically. Well, here's where a spiral sink would fall. But again, we don't want to extend that analysis to points that are not close to 0, 0. So this is not going to tell us anything about the dynamics over here, for example. And so if I want to do this, then what I would need to do is linearize the sine function now at pi. Okay, which is going to be a totally different thing. And then we would want to use that linearization again to try and figure out what's going on there.
Would you mind zooming out just slightly?
Mm-hmm. So to take this in a more general direction in a second, so we're going to have to do this process separately at every equilibrium. That's the kind of one drawback here, is that it's just a local analysis. Okay, can I scroll down? Okay, so let's come up with a general plan of attack for these now. So we'll kind of do our usual thing. I just want to motivate where this process comes from before I just spring it on you and say this is how it works. So what's going to be key here is how we can linearize functions that maybe depend on more than one variable, for us, 2 variables. And this is what you guys did some reading about for the quiz on Monday. So this is exactly that same formula for how do we linearize a function of 2 variables. And this is where we calculate the partial derivatives. And so this is very similar to the example where we have just a function of just one variable, except now we need to include information about what is the slope in both the x and the y directions. So here's another system. So let's say I want to think about this system over here, and this is non-linear system because of the top equation. Bottom one is actually okay. So let's think about, okay, I want to linearize this system in order to think about whether equilibrium are stable or unstable. So it kind of goes unstated here, but kind of step 1 would be find equilibrium. By setting both of those equations equal to 0 and solving. And I'll kind of skip that step in the process because we've done that previously. But in this case, we had that on the last couple of homeworks. In this case, now we're no longer getting one equilibrium at the origin. So here we have two equilibrium, neither one of them at the origin. And so let's say I want to think about, is the equilibrium at 1 minus 1 stable or unstable or semi-stable, or what is the deal with that equilibrium? Then what we're going to do is linearize both of those equations at 1 minus 1. Here's how we can do this, is we're going to let x equal 1 plus u and y equal minus 1 plus v. And so what you can think about of these u's and v's are, these are telling us, like, it's like a dx and a dy, like how far am I deviating from the equilibrium in the x direction? That's what u is saying. And how far am I deviating in the y direction from minus 1? That's what v is saying. So you should think about u and v as being really, really small numbers. Okay, and so we are going to then linearize both of these equations at 1 minus 1. So I'm going to call this equation up here, oops, f of x, y, although it really only depends on x. And I'm going to call this one over here g of x, y. And these are two functions, generally speaking, that could be of two variables, x and y. And so we're going to come up with the linear approximation for each of those. Okay, so how we can do that, again, is using this formula over here. Right, so that's the formula for the linearization of f at 1 minus 1. And the reason why 1 minus 1 was picked, again, is because that's in equilibrium. Sorry, this over here should be evaluated at 1 minus 1. And so this is exactly this formula that's highlighted in yellow above. So f of x, y is 1 minus x squared. What is the partial derivative of that with respect to x?
Negative 2x.
We're going to get minus 2x. And what would the partial derivative of that be with respect to y?
0.
Is 0. So these are the values that are going to go in place over here and over here. So we're going to use this information to fill in those values. So I found formulas for the partial derivatives, and now I evaluate them at the equilibrium. So plugging in x equals 1 into this, I get a derivative of minus 2, partial derivative of minus 2. Whoops. So I evaluate my partial derivatives at 1 minus 1. I evaluate the function at 1 minus 1. And let me just say, because 1 minus 1 is an equilibrium, we know that when I plug it into this, I should get 0. And when I plug it into this, I should get 0. So that's why when I evaluate f at the equilibrium, I'm going to get a 0 over here. Okay, any questions about that so far? So let's see, when we group this all together, we are getting a minus 2x, and then we have plus 2 over here. Is that right? Okay, any questions?
Could you repeat your statement about why the f of xy is just 0, the equilibrium point?
Yeah, so if we could always just plug it in to check that, but if I take 1 minus 1 and plug it into this equation, I would get 1 minus x squared is 1 squared. That just gives me 0.
Sorry, my bad. Thank you.
Yeah, so you can kind of, you're welcome to check them, but I'll just mention that these, you should wind up getting 0 for these exactly because that's where they kind of came from in the first place, is they were values that made both of those equations equal to 0. Okay, and then we could do the same for G. Where now g of x is going to be, g of xy is this minus 3x minus 3y. So we can take the partial of g with respect to x. That gives me minus 3. I can take the partial of g with respect to y. And that also gives me minus 3. And then I could evaluate g at 1 minus 1. And that gives me 0, right, as it should. And so for the linearization here, I would get partial of g evaluated at my equilibrium point, which here I would get minus 3 no matter where I evaluate this. And so we get minus 3x times x minus 1 minus 3 times y plus 1. Okay. Any questions there? Okay.
Any
Yeah.
reason why we got the same formula back?
Yes, because if you linearize something which is already linear, then you should get the same thing back. So we already had something linear. So this was kind of, yeah, not the most interesting thing to linearize because it already was linear. But yeah, we definitely want to make sure we get back the thing that we started with. Okay. And so now what we're going to do is rewrite this system in terms of U's and V's. So I'm going to replace my X's with 1 plus U, and I'm going to replace my Y's with minus 1 plus V. Okay, and the reason why, it's like we're sliding this nonlinear system, which has an equilibrium at 1 minus 1. We're going to kind of think about this as U and V are telling us like how far away are we from the equilibrium. So in some sense, it's almost like we're transporting this equilibrium over into a different universe where our variables are going to be U and V, and U and V are representing how far away are we starting from the equilibrium that we are interested in looking at. So now we can go ahead and let me plug in this for X.
Could you use 1 minus, I mean, yeah, 1 minus U and then 1 minus V, negative 1 minus V if you wanted to?
Sorry?
Would that, if you wanted to do 1 minus U and negative 1 minus V, would that still work?
Yeah, you could do it that way, sure. Usually we think about these things as like U and V being the distance from the equilibrium. Yeah, you could add it or subtract it. I'll just say it. You get unnecessarily more negative signs if you want to subtract it. And so when I plug 1 plus U in up top for this one, let me just do it over here. Right, that just gives me minus 2U. The constants cancel out. And for this one, if I do the same sort of thing, I'm going to plug in 1 plus U. And then over here, we're going to plug in minus 1 plus V. And again, constants cancel out, and what's left is just going to be minus 3U minus 3V. Oh no.
So with the linear one, we didn't have to do the LX kind of thing. LG of XY, we could have just done the, could have just left it as linear and plugged in the 1 plus U and 1 minus 1 plus V.
Yeah, I would say that most of the time we're not going to have things that are linear. So it doesn't hurt to go through the process just to make sure you get back the same thing. But yes, we should get back the same linear thing if we started with a linear thing. Okay, so what this allows us to do is just rewrite each of these equations in terms of like, how can we express these in terms of functions of X and Y? We're going to express these in terms of functions of how far are we moving from 1 minus 1. So So we have x, y are 1 plus u and minus 1 plus v. And so we've kind of talked about how we can rewrite this side of the differential equation. And let me also get rid of the x and y's on this side of the differential equation by taking the derivative of these. So if I take the derivative of both sides of this equation, we see that dx dt would equal du dt. And over here, we see that dy dt would equal dv dt, right? Since all we're doing is shifting these things. So adding a constant to x or y isn't going to change its derivative. So that gives me a new linear system below in terms of these new variables that we introduced, u and v. And so in case you're kind of curious, this material is in chapter 2. This is like section 1 of chapter 2. And so we took this system that we started with, dx dt was 1 minus x squared, y dt is equal to minus 3x minus 3y. And by doing this change of variables, we're now able to rewrite this as minus 3u minus 3v. And let me just say, this is a good approximation as long as u and v are both small values. And so that gives us a matrix of coefficients. And then from this, we can calculate eigenvalues of this matrix. And I'll just kind of, that's a pretty quick calculation. The two eigenvalues here are minus 3 and minus 2. So the equilibrium at 1 minus 1 is a stable sink, since we have two real negative eigenvalues. So what that picture might look like in the phase plane is if we are looking at this point at 1 minus 1, it's a stable equilibrium. And what I know is, at least if I start near this point, things should be heading in towards that point. I don't know what's happening far away from that point, but at least this tells me solutions that start near that equilibrium are going to stay near that equilibrium. So kind of the advantage to this process is we didn't really need to introduce any new mathematics. Maybe reviewing that linearization process is an adjustment, but how we do the equilibrium analysis, the stability analysis hasn't changed. We just need to do some linearization in order to get that matrix, in order to get the eigenvalues. Okay, any questions?
Yeah, can you go back up where you were replacing the u and the v's with the derivatives?
Hold on 1 second. I'm switching to headphones. What was that question?
It was like one of the previous steps where you had the like dx dt, and then you took the derivative of both sides with respect to t. Like, just scroll back up.
Yep.
So keep going right there. So classify the equilibrium point. So when you get that point right there, how are you getting x and y equals that? Like, I think I missed something.
So that was from here.
Okay, and then you found the, okay. So,
Yeah, so we're gonna take, yeah, so we're just gonna take this differential equation, which is in terms of our original variables, x and y, and we're gonna re-express it in terms as a system of differential equations in terms of u and v. Like, how far are we moving from this equilibrium? And so we need to replace all of our x's and y's in terms of u's and v's. And so up here is where we linearized and then expressed the linearizations in terms of u and v using this substitution. And then down here, we just said, well, we also want to replace dx dt and dy dt with their equivalents in terms of u and v. And that's what happened in this step over here.
Okay. All right. Thank you.
Yep. Okay, so let's see what happens now at the other equilibrium point. So this system, same system, had 2 equilibrium points, one at 1, -1, and one at -1, 1. So if we wanted to do this process, kind of like first we find the equilibrium. That's step 1. So now we're on step 2. And that would be, let's kind of introduce variables u and v. So we're going to let x equal now, whoops. Right, we now adjust how we are going to define x and y. We're going to move a little bit away from not the point at 1, -1, but now a little bit away from the point at -1, 1. Okay, we're going to use the linearization of these same functions at now -1, 1. Okay, and that would be this process of finding the partial derivatives and then evaluating them at our equilibrium point. Okay, and here the difference in now and what we did previously is now we're going to evaluate these partial derivatives at this different equilibrium. Now I get a partial derivative at that equilibrium with respect to x gives me +2. This one still gives me 0. Okay, so here we're mimicking how we did the linearizations in the previous one. So these partial derivatives, sorry to leave and come back, just come from the same work that we did over here. So any questions how we got those linearizations? Okay, and then to finally get our polished off linearization written in terms of U's and V's, we would then substitute those into these linearizations. And now we're going to express in terms of U and V instead of X and Y. So let me just kind of continue working down over the space in part B. So this would mean that the linearization of F would be 2 times, and then I'm going to replace X with -1 plus U. That gives me 2U. Okay, and all we're doing again at this stage is just using this substitution for X and Y. So all of these X's are getting replaced with -1 plus U, and all of these Y's are getting replaced with 1 plus V. And what you should see happen when you do this is you should get a perfectly linear thing back in terms of U and V. So notice I don't have any constants left in either of these equations. That's the way it should always work out. So if I had like suddenly like a leftover 7 over here, I must have done something wrong. Your constants should all cancel out when you're doing this linearization process at equilibrium. That's what's special about the equilibrium. And so now we've got our system. The UDT is 2U. The VDT is -3U -3V. And if you calculate the eigenvalues for that system, that linearized system, we get different eigenvalues. We have a +2 now and a -3. So that means the point at -1, 1, this must be a saddle. Any questions?
Is there a reason why you flipped the X and Y, switching over from U and V? Instead of X equals 1 plus U, you have it as -1 plus U. You swap the other sign for the substitution of Y, so it looks like it comes out to the same thing.
So the equilibrium was at -1, 1. So the
Okay.
-1 here comes from the X coordinate here. And then the positive comes from, so that's why we have different signs, is because of the coordinates of the equilibrium.
Got it. Thank you.
Yep. So to come back to the picture, so this told me from kind of the first analysis that we did, 1 minus 1, that had 2 negative real eigenvalues. So that was a sink. Everything was going into that equilibrium. And now if we come over to -1, 1, and we were to look at that point, let me just say, we could be more careful about this and find like the eigenvectors so that we know more carefully which directions are going in and out. But maybe what we do know is these might not be the exact right directions, but we do have some things that are going in and some things coming out. So what I can see is that over here, we are getting a bunch of saddle, or we have a saddle point. Yeah, I actually can see that I drew it slightly off. So I think it would look more or less something like this. And so then we can kind of piece together these two separate pictures that are happening at these two separate equilibriums. But this analysis is just a very local thing. So for each of these, they're only telling me what's going on, like in a very small neighborhood around that equilibrium. Okay, any questions? So it's a long process, and so let's streamline it. We can do better than this. And so this is what comes up with this notion of a Jacobian matrix. So these come up in all different places in mathematics, and this being one of them. So let me just kind of make a couple of observations. And so we were looking at, in the example that we looked at, we had the x dt was 1 minus x squared, and dy dt was minus 3x minus 3y. And a Jacobian is a matrix of partial derivatives. So we're going to call, again, the differential equation for x, f, and the one for y, g. So the Jacobian is a matrix of partial derivatives. We line them up as follows. So in this case, our partial of f with respect to x was minus 2x. Partial with respect to y was 0. This was a minus 3, and that was a minus 3.
You put g of x twice.
Ah, thank you. Yes, that should be a y. So in general, right, these partial derivatives, they depend on x and y. So we might get expressions that have x and y in it. This was a little bit simpler because these formulas were a little bit simpler to start with. And then we could evaluate the Jacobian at each equilibrium. So we had one equilibrium at 1 minus 1. And then we would just plug in that into for x and y in our matrix. And that gives us a matrix of minus 2, 0, minus 3, minus 3. And then we could evaluate the Jacobian at our other equilibrium. And that would give me a different matrix that has different eigenvalues, generally speaking. So if we kind of go back and look at the work that we did, for the first one, we kind of went through this process of linearizing it, substituting things in, grouping our terms together, et cetera, et cetera. All of that work brought us to the fact that we had a matrix of minus 2, 0, minus 3, minus 3, right? Which is the exact same matrix we got just using the Jacobian. In the case when we did it at minus 1, 1, we went through this whole process, all of which just to figure out that our matrix here was 2, 0, minus 3, minus 3, which both of those results are consistent with if we had just used the Jacobian, we would have gotten the same result. So I didn't want to just spring this Jacobian on you and just say, look, it's magic and it works. But what's actually going on is a whole bunch of machinery in the background. We're linearizing things, we're simplifying, et cetera. But this Jacobian gives us a nice way of maybe streamlining that work. So when you're doing these, like we did it in this part over here, we could much more simply just condense all of these steps into saying, here's our system. We're going to find the equilibrium. We're going to compute the Jacobian matrix of the system. We evaluate the Jacobian at each equilibrium. And then we go ahead and find the corresponding eigenvalues of that Jacobian. And then if they're real, complex, positive, negative, we have already talked about how we can then classify that type of equilibrium. So that hasn't changed. Okay, so hopefully this gives you some gist for how to get started. Maybe what I'll do for you guys is just write up like what a solution might look like for the first one that we started with, using a Jacobian, just to compare it what that would look like. So if you want to get started on your homework, you certainly can do some of those nonlinear systems. I pushed it back to Wednesday next week because I figured I figured correctly that we could use a little bit more time on Monday working with these. So that we'll do that. And then once we feel comfortable with these nonlinear systems, we're actually going to start some new material on Monday that's not going to be on your exam. So that we'll be working in chapter 6 in the reading materials, dealing with Laplace transforms. So that's what we'll get into next week. Okay, well, thanks everybody. If you have any questions, I have office hours tomorrow, 10:30 to 11:30. Otherwise, have a nice weekend, and I'll see you guys on Monday.